So the motor one chapter mainly discuss about the basic DC motor. Motor two, we start to look for other more advanced, more practical motor which being used in EV. Motor one are basically those motor used in golf car, really simple EV system. So here we're going to learn about the PM, permanent brushless DC motor. We also learn about induction motor and SR motor. So this is more commonly used motor in electric vehicle system. So let's go through what it is. So first of all, which one is the highest speed motor in the world? Which motor is higher speed, top speed? Do you think DC motor, induction motor, induction? What do you think? How about this gentleman? What do you think? High speed of the motor in the world? This is DC, right? How about what do you think?
Yeah, brushless,
Okay. The high speed motor is switch reluctance. Why is that? Because for switch reluctance motor, there isn't any winding or no PM on the rotor. But brushless DC, we still have PM in the rotor, quite heavy, quite bulky. So brushless DC motor, once you have the motor, once you have the PM permanent magnet, you cannot be too high speed. We need something really light rotor to become high speed. So that's something you need to know that. Although many vehicles still using PMO motor, PM brushless, but still the high speed motor go to the SR motor. So is the PM motor a better? I think we have been discussed this topic. PM is really good because we don't need to worry too much about the PM, the magnetic field. So that's why we usually have higher power density. But having said that, high power density, that means you can be smaller, and air gap can become also not that high requirement. You see the rotor stated between them, we call it air gap. This is one of the critical design for the motor system. So we got for example, right? And then we got so between the motor and stator, this is called the air gap. So the magnetic field will go through here. So in theory, if the air gap is smaller, then we got stronger magnetic power to become our motor. So that's why many motors try to design air gap to be small, usually about 0.5 to 1 millimeters. That's quite a good standard. But the thing is, if the motor gap is so small, in case anything varying vibration, you touching each other will become a disaster. So that's why air gap is design must be really careful. Cannot be too small, or we like to be small, but cannot be too small. For PM, because the magnetic field is so strong, so the air gap you are able to go up to about 1 millimeter. But for other motor, like the switch reluctance induction motor, we have difficulty to enlarge air gap. Otherwise, the efficiency of motor is not very good. So probably 0.5 mm. So these are not the rule of thumb. So 0.5 mm to about 1 mm. You can see that it's really thin, kind of. So the alignment of the motor, the shaft alignment is really complicated. Yeah, we need to do it really well. And we need to put some bearing there, make sure they align really well. So that's the thing we need to look into. So, and then how to control motor speed? Of course, we mentioned to you, we use inverter to control motor speed in a typical way. And then how many regions of motor that we say 4 regions, 4 quadrants on control. So we just use the control motor, about 4 quadrant motor, quadrant 1, 2, 3, 4 to operate. Anyway, so today we already discussed about session 2 about DC motor. Now we're going to discuss more about the PM, permanent magnet, and then AC drive, induction motor, switch reluctance. So they are all the popular motor drive system for EV. So now let's look at the permanent magnet motor. So there's many professors, many electronics try to classify the PM motor. Many names, you can see there's so many different names called DC, or PMO motor. So basically, we can also classify them into PM DC motor, and PM AC motor. So that is to say mainly about input side, we tend to inject them with DC voltage or inject them with AC voltage. So that's how we define that. Again, the PM brushless, like what we mentioned just now, you all like to have the brushless DC motor. So also really common one. But the thing is, all the PM brushless motor at the moment, we mainly see them to use in some small vehicle, maybe also in a cooling system in your microprocessor, computer microprocessor, your fans are using brushless DC motor. It's very common. But for large, really, really large vehicle, truck, huge vehicle, we may have difficulty you use DC brushless. Why is that? SUV, local private car, quite okay. But how about for truck, big truck, electric ship? Can we use PMO motor? In theory, we can, yeah, because the PMO is supposed to be higher in efficiency, more effective, right? Higher power density. So for big vehicle, we should use PM, but that's not the case. Why is that? Why PV don't use them for large vehicle, really large, huge vehicle? Why is that? Have you seen any big vehicle using PM? Seldom. What do you think?
I think some PLDC model may supply less torque and some specific application. Less torque.
Brushless DC, we get able to make it design to get high torque. I think I can design PM motor with high torque without any difficulty. It's not really a torque issue, it's another issue. More in the industrial.
With the power,
something with the power rating. You see, SUV vehicle usually about 100 kilowatt power. And then if you go to a truck, they usually 300 kilowatt, 500 kilowatt high power. Then it ends up to be the PM permanent magnet will be also quite large and be quite big. PM are using unborrowed rare earth material. They're very expensive. That's one thing. Second thing is, if you want to make a large PM, you see the PM is really large there, so big in any one of the pole. Then to form PM, you need to pressurize all the powder iron, iron-boiled powder iron to confine them in small size, pressurize them so the machine to make the PM for high power large is really expensive, really difficult. So that's why we have difficulty. We can, but really expensive. You won't get a really large pressurizer. But that size of PM, the pressurizer will bigger than this room to make only one PM pole. You need to many of that. So that's why it becomes difficulty when you use PM motor for really large machine system. So that's why in the market, when you try to search for the brushless DC motor PM, use small power. You can search up. I don't think you can see anything megawatt power. Impossible. Too expensive. Nobody will do that. For such large power, induction motor is good enough because they don't care about that 1% efficiency better. PM motor, you can able to have more than say 96% efficiency, maybe 95. Induction motor may be 1% less. So we don't care about it. If you can cheaper, a few times cheaper. So what's the point to use PM? Only for some really dedicated equipment like your microprocessor cooling system, they want really high performance, high speed. That's why they use PM. PM brushless, they can have high RPM, high speed of rotation, more than 10,000, no problem. So that's why they tend to use the PM. But for heavy duty, is probably still too expensive to do that. But anyway, so that's how the PM history, like. So the key advantage for PM, I think you can all know them fine by now. And high power density, we don't need any motor winding. the motor itself will become a PM. We stick the PM into the motor. We still need the state winding. The state winding provide the basic thrust. And then this basic thrust interact with PM will provide with the thrust interaction, become our rotating torque. But that's why if the motor winding is good, then I mean you can reduce some of the copper losses. You can also reduce the weight, reduce the inertia. So that's why per minute can have high speed of rotation. So that means all the power loss are mainly come from the state winding. The state winding is mainly copper there. We have the copper loss over there. And PM is now has been manufactured for many years. So they really have a really good skill for the manufacturing, for the production. So the defect is getting lower and lower now. But again, we stick the PM into the rotor still quite a technique because rotor is now rotating. I mean, to stick the PM there, you cannot ensure that they can, after 1 year, 5 years, still able to have a constant air gap without any defect. So it's good because you have low inertia. That's why the acceleration, the speed up is also really good. The dynamic response also really fast because you can speed up really fast, low inertia, so dynamic performance must be good. And we don't need to design any fast coil, we don't need to design the external separate fast winding. Everything becomes easier. We only need to excite them with free wire of the stator winding. That's it all. So that's why this kind of motor become popular. So basically, that is how it look like. So the motor will be in here. We got 3 sets of the winding. And then on the left-hand side, we got motor joint. So this motor joint is different from H bridge. We call it full bridge or the 3-phase bridge. So we got 1, 2, 3, 3-phase to connect it to the 3-phase winding here. So you can imagine the 3-phase winding more like this. In here, I only give you really basic principle for the motor. You don't need to understand too much about it. But if you go to my machine lecture, I will teach you more about what is a brushless DC motor. So basically, this 3 winding, we got 3 type winding in here, then probably is something like that. Basically, something like that. And then yeah, there's a 3-phase. Internally, we can connect the winding into this called star connection. Or some people will like to connect it into delta connection. That also be feasible. So there's many different ways we can do the connection. And each time we use this transistor, for instance, we turn on this transistor to high voltage. And then this B, we can turn on this transistor. So between A and B point, we excite them with a DC voltage. We can also do the switching. And then, so the PM will be more like in here, the PM in here. Then the thing is, we need to energize the winding, provide the magnetic flux to interact with the PM flux to provide you with the rotating torque. So that means we need to know the position of the rotor. So we usually for all the PM, you got sensor to sense position. We only sense when the PM rotate to certain polarity, we turn on the corresponding phase to excite that. So for PM motor, this time, we need the sensor to sense the position. So that's how it looks like. So typically you can see that this motor still basically look like DC motor. It's a DC motor anyway, but it's just putting the motor inside out. Before DC motor, the PM is outside, the winding is inside, is the commutator. But now we flip it inside out, the outside become a winding, inside become a PM. So they do it another way. So that means each is still have some winding in here, but some winding resistance also have its own back EMF. So the motor equation is the same as the DC motor equation, exactly the same. So this one will show you a star connection. And it's getting complicated now, but just show you the waveform. I will not examine you about this. but just show you the waveform like that. So what we try to do with it, you see we got three-phase IGBT inverter system. You turn on some particular phase to make the waveform will become kind of square wave, but not exactly square wave, become a kind of the closely square wave. You turn on, sometimes you turn off, becomes 0 volt. So this waveform, you can see that each of phase A, B, C are displayed by 120 degrees to next of the phase. Because phase motor, each of the phase voltage or current will display by 120 degrees anyway. So that's why we use this method to do that. If you study more, then we have the pulse pattern to drive them. So we turn on transistor 1, 3, 5, 2, 4, 6 in this manner. There's some special pattern to drive them to rotate the motor. So you can see that how we do that, we can label and rotate each of transistor 1, 3, 5, 2, 4, 6, this pattern, and then use this special pattern to drive them automatically. Then the motor will have really good forward rotation. How to drive them is not covered in the lecture. We'll cover my next lecture when you come to my course, electrical machine. But that's the way how we control them. So all the pulse pattern already defined in all the motor drive system. And then for the control for this kind of the DC motor, quite straightforward. We have a DC battery here, pass through a three-phase inverter to go to motor drive. And then we need to sense the voltage and the current. Why we need to sense current? The current highly related to the motor torque. If we want to speed up, then we need to provide them more torque. So we need to use this controller to control it to have more current. So the control system will generate the pulse pattern and then go into the inverter to design which transistor to turn on and turn off. So that becomes the overall system. How the speed rotation, because when you generate pulse pattern, you can generate A, B, C, and then looping continuously. And then you need to tell them the frequency of the rotation. So that your frequency demand will tell what kind of frequency the motor should be rotating. So basically, to control this motor, you need to control the motor torque, which by the current, and also control by speed, torque and speed control system. And then just now I mentioned only a three-phase simple one, but in fact we can extend to multiple phase, like in here. So each of the phase are controlled by two transistors. You see, when we have a multiple phase in such a way, then the torque ripple between the phase can be minimum. For electric vehicle, then hopefully we try to use multiple phases. Firstly, because high power, each phase only responsible for a portion of power. For instance, total power motor, each phase only 1/3 of power. In this case, we can share many of the power in each type of transistor. You can see in here, we are using many phases. Because in motor have so many phases, even though one phase by accident is broken, the other phase still operate. It's just in here we got more ripple torque. The motor is more rotating. It won't suddenly stop. So when the motor rotates away from this broken phase, it still can able to continue the operation. So that's why I tend to use multiple phases. That would be more advantage. So that's how a pedicle motor look like, how a real multi-phase brushless DC motor shall be. And then now we finished about the brushless DC motor. Another way we look into about the AC motor drive. AC motor drive will be if a motor here. Then we are using AC voltage to excite the motor. Then you ask me, how come the circuit look really much the same as DC motor? Yes, what you say is right. But DC motor, we are actually providing a DC into each of them. But for AC motor, these two voltage, actually we have some modulation to moderate the voltage waveform looked by an AC waveform to excite on the motor. For instance, if you turn on A and D, turn on these two, then the motor voltage across these two will become like this. And then you turn on B and C, the motor will be reversed and so on. So that's how you can program a square wave excited on the motor. So that's how the motor system. So you can see that that is a square wave, but still an AC waveform, but just a square wave AC. It's not DC. If you look into this harmonic, you can see that the fundamental of harmonic will be still like that. Still really much look like a harmonic. But it's, of course, it do have another low order harmonic. So that's to say, you can still excite them, you can still see basically a more sine wave into here. So that's to say, we can control the transistor to control this sine wave amplitude and frequency, so that we're able to control motor voltage and motor rotational speed. This is only simple topology to show you, but in fact, when we have real application, we will using this simple square wave. We use another high frequency quality pulse with modulation. We're going to change that one into more look like this one. More pulses, more high frequency. And this waveform we call it pulse width modulation. So of course we know PWM. So that's the name we usually do. Later on we'll show you more about PWM. So that's how we can see that how the waveform will become more look like a sine wave. Once we use high frequency waveform, you can see that the voltage appear will be still more look like sine wave. That's how we use PWM to generate sine wave so that it make it look like a sine wave. So that means although this motor called AC motor, we can actually using a sine wave to excite on a motor. But for VH vehicle, we don't have any AC source. We only have DC source. So DC source, we're going to use this PWM to make it more look like a pulse pattern close to a sine wave. And then the motor itself, they don't understand PWM. They only know the average voltage. When the motor see the average voltage look like a sine wave, they will just go for a sine wave operation. This frequency are really high frequency. So that means we control pulse width and duration, then we actually can control the amplitude of the voltage and also the frequency of the voltage. The motor itself is not that careful, it only understands the average voltage. So that's good enough. So that's why we use PWM, we are able to control AC motor. So that's why we still call this the AC motor drive system. The pulse pattern we generate is sine wave PWM modulation. We call it sine wave. Sinusoidal, I think you heard about this. Sinusoidal PWM. So that's how the system actually look like. Okay, let's clear it. So that's how I actually say, I want to excite the induction motor using a sine wave like this. So that means each of the transistor, we need to control turn on and turn off time, so they can make it become something like this kind of the pulse width modulation waveform. So if you look at more detail, you can see that this still carry a sine wave, this kind of the pattern. So that means we're not actually giving the motor with a sinusoidal continuous waveform, but giving them chopped PWM waveform. So we use this method to make the motor feel like being excited by something. So that's how the actual happening. The thing is, in power electronics, we only turn on and turn off the transistor. That's why we cannot create anything pure sine wave. We can only fully turn on, fully turn off. So by using fully turn on, fully turn on, fully turn off, that's only two states for this power converter. To make it look like sine wave, we can adjust turn on time here. Maybe at 90 degrees, we may want to have higher voltage, higher ambient voltage. It's turn on longer time. We use the duty ratio to make it become look like more voltage. In here, we use duty ratio, make it less voltage. So that's why still look like a sine wave, but using the pulse width to emulate a sine wave. That's good enough for the motor. The motor is don't understand what kind of item we put in, only know the average voltage. So that's how it look like. Okay. So when I turn on the motor winding, the current will therefore increase. When I turn off, the current will therefore drop, decrease, and turn on, turn off, turn on, turn off. So in theory, we turn on, and can control how the waveform look like of the motor winding. So that's why motor winding can still control it to be a sine wave. Become AC sine wave waveform by using the pulse width pattern. So this pattern, once you observe this one, this is our sinusoidal PWM. The current will therefore will look like this. Here I'm using really low frequency to show you the operation, but in fact we are not using this frequency. This frequency too low. We use it using at least more than 20 kilohertz, 100 times higher than the sine wave. So in this case, once we 100 times, this ripple become so small, really look like a sine wave. You will need to use amplifier to check that's a sine wave, right? So that will be really, really small in the actual condition. Okay. Up to this point, any question?
How we control the pulse? Like we see in the center, it's quite closer, and at the end, it is like spacing is little wider.
Yeah.
Just to control.
We have some equation to calculate this pulse rate. There's some formation here. But of course, it's not covered in this lecture. Again, if you go to my lecture in the actual machine, I will show you how to do that. It's very simple equation. You go to any website, we've got something called sinusoidal modulation PWM. That's the topic you can search up. The equation really much to use sine wave to become a pulse wave. Again, in here, you can see that there will be some delay due to the PWM, but actually when frequency become really, really high, that delay only become 1 second. So it doesn't cause you any delay. So that's quite okay. So that means for 3C motor, and this one of the display to show you how we can use a no PWM, simple waveform to excite on a AC motor. So assume that's our AC motor. We connect them into 3 phase. We can use PWM I showed you just now, but you see when 15 years ago, when we don't have PWM technology, we only using really slow frequency to drive an induction motor. So during that time, you can see that if I energize each phase A, B, C, in each is placed by 120 degrees with that square wave, and then using this pulse pattern, and then we calculate the phase voltage. You see this winding, it does not connect to the phase voltage, only connect to the line voltage. There's no 0 point here. This is the phase voltage. Between these two is the line voltage. So this line voltage is this voltage minus this voltage. Okay, so that's why for the motor winding between these two, you only understand these two voltage. So which will be, say, A, this minus this one will become this voltage. So the voltage waveform appear across here will become this one, appear across these two winding will become this one, appear across these two winding will become this one. So you can see that this waveform, although is square wave, but do have some kind of the fundamental component for sine wave. So you can see that. Let me do some sketches. You can see that this is still more sine wave, right? This still looks like sine. So that's how we using this pulse pattern to generate sine wave applied to AC motor system. So this is really fundamental voltage generation. 50 years ago, when we firstly conduct the power electronics, how we're able to generate some simple AC waveform. You see, power electronic cannot produce perfect sine wave. It can only produce square wave. But that square wave will give us a really good fundamental sine wave pattern, although with some harmonic. But that's the way how we control AC motor. So using this concept, you can therefore understand why we can use power electronic to drive motor. You see, power electronic, we are not trying to use power electronic to produce a sine wave. We don't do that. So that's to say, we got battery voltage here. And then we use this kind of inverter. And then connect to a motor. Connect to a motor. So bear in mind, we in here, this voltage is only this one, only this kind of pulse pattern. We don't produce this one. We can't. Power electronic cannot produce a sine wave. We only produce this, which is that one. If you want to produce a sine wave, what you need to do is to put a filter in here. You can still do that, LC filter. Then the motor will experience a sine wave. So in all the integral joint, including your EV or your home inverter, whatever you like to do, or grid connected PV system, you have inverter, they don't produce you pure sine wave. They can put a few filters like. So when you buy an inverter, you need to specify do they include filter. Some of them they call it the pure sine wave inverter. That means they give a filter to give you pure sine wave. Some of them they only give you this PWM. But the question is, why we don't need a filter to drive motor? What do you think? Now we drive an EV, or maybe industrial drive in your manufacturing plant, you need to drive some motor. We just use an inverter. We don't use sine wave inverter. Why is that? Because of this. Yeah. Why? Because this pattern is sufficient to drive your AC motor. Or when we use an inverter, the pulse pattern come out will be this kind of chopping waveform, not a sine wave. But that will be good enough for us to drive a motor. We don't really need to put a filter first. In theory, you may think, I like to have a filter to make it look like a sine wave, filter all the chopping waveform become sine wave, and then go to a motor. That's a perfect. But we don't need to do that. Why?
To reduce cost.
Yeah, of course, reduce cost is a really good answer. It must be a good answer. Of course, when you tell a boss, I just reduce cost, I don't care of the sine wave performance, still not a good answer, but it's good enough. The main reason is you see the motor so big. Internally, there are many winding. The winding itself already a filter. So this is already a big inductor. So you don't need that additional wasting your money. Instead, inductor, they will automatically filter all the chopping waveform become the sine wave. So that's why when you measure the current of the motor, it's still sine wave. So when you measure this current, if this current still a sine wave current, because this is a huge inductor inside. Okay. So that's the vision for all the integral drive, not necessary to put a filter. The filter already inside the motor. Okay. Save the money. So now then, go back to the basic motor drive system. That's how the drive system shall look like. And we look at the battery input for the battery system, go for PWM inverter, and we drive an industrial motor. So this motor, you can go for, if it's using single motor, then we're using a differential gear to connect the shaft. Sometimes we may need to put some kind of the gear in electric if we need to. And then, of course, we have PWM system will be controlled by the microprocessor, generate our pulse pattern. And then we also need to feedback from the motor speed or your driver demand for how much power you need to give out, how much speed for the vehicle. So that's basically a very simple configuration to show the operation. So PWM we've been talking about for really 1 to 2 class now. PWM is really typical name we use for most power electronics, pulse width modulation. But sinusoidal PWM is the one we have been using for really community use. So everybody uses this one. But actually, there's many other different kind of the PWM being used in the type of CVP. Very different kind of the PWM. That's only for the technical journal paper. But for real application, we tend to use this one, or maybe space vector also really popular. This, I think nowadays many of motor drawing are using space vector modulation. And nickel area also be used. Distance band not that popular. So most popular will be only these three are being used in the industrial drawing for the motor system. So that's how the waveform shall look like. You can see that, again, we mentioned to you, we are using the time duration to control the voltage. We cannot control the peak voltage. The peak voltage equal to the DC battery voltage. Then we only control the width. So that's why we call pulse width modulation. So for instance, for sine wave in here, I want to have more voltage. We just extend the pulse width to have more voltage. And then we want to have low voltage, minus 70 degrees, then we reduce the pulse width to be really small. So basically, that's so-called the pulse width modulation. Then we can do the adjustment. So again, there's so many different types of the PWM. So I don't go through too much detail about how we conduct the modulation. But in the future, when you come to my class, I show you more detail about how the modulation looks like. But basically, we're using the time domain to adjust the voltage to do the job. Nickel area means if you're trying to look at sine wave to a motor, the motor itself only understands the volt and second. Voltage times second is some critical important for inductive system. You see, I think you all know the basic equation L equal to V. That's all basic equation. What that equation means is L di equal V dt. So this term, we call them the volt second. As long as a motor winding have this kind of the same kind of this thing, then the induction time is that one will be more related to the magnetic thrust that the system can able to receive. So motor winding itself, they only need this amount of the magnetic thrust. That is good enough. So that to say, if you can control your waveform so they can provide you same kind of the area, then it doesn't matter this one or that one. If this area equal to this one, the sine wave area equal to the Peter area, the motor itself will consider the same kind of magnetic thrust. The motor will behave the same. They don't care. They don't understand. They're not human. They don't know what waveform. They just know volt second, the thrust is the same. Volt second, it is the thrust. So the distal motor, driving Peter M is same kind of thrust, driving sine wave, same kind of thrust. That's good enough. So that's how the basic concept for the pulse width modulation. So here will be some other sample to show you the pulse modulation for three phase. The three phase, you can see that this figure F, you can still sketch sine wave. So these two sine wave are displayed by unchanged. So for a three-phase motor, one phase we use that square wave, the other that one, that will automatically give you pulse width modulation. The same format as the sine wave excitation. So that means your induction motor, you can use our three-phase voltage review, our three-phase in the building, we can energize them. But however, we can also use inverter to produce this kind of three-phase PWM to drive them, the same kind of performance. The only one will be different. If you use a pure sine wave to drive a motor, or to use PWM to drive a motor, what is the major difference you can observe? Inferior, they're the same, but there's still one difference. Although the flux for two times will be the same, the only difference will be the power loss. This one, we are using high frequency. For this frequency, at least 20 kHz, sine wave 60 Hz. So you see high frequency, the motor winding with higher AC losses due to skin effect, proximity effect, or core loss. So the motor will get hotter. So if you touch a motor, you can see that it gets so hotter than other motor. That means this motor is driven by PWM. If it's excited by sine wave, you won't get that hot. In many industry in the past, they tend to have more energy savings, and then they try to use inverter to replace all the sine wave operations. Once they change the inverter, the motor will get hotter because they're using PWM. So in this case, you need to ensure your motor will be survivable for PWM. Some motor, they're not really good for pulse voltage because generate high dV/dt. What that means is, if you go by the basic equation for the C dV/dt equal to, what that equation means, your motor winding, you got many or the copper winding, there will be a copper, they call it enamel copper winding. Between the winding, they got enamel coating to isolate each of winding, each from other. So you got one wire here, one wire, you got many turns here. They are isolated by the enamel, insulated. So if you got high dV/dt due to that kind of thing, then there will between here, winding there's some small capacitance, parasitic capacitance. Just like in here, these two, they're isolated, but between these two cables, there's some capacitance. Although small, maybe picofarad, still something. But when you have a high dV/dt like in here, they generate some mid-gauge current between the capacitance. Then that will cause breakdown. So that means if your motor winding, the coating is not good enough, you cause the motor winding breakdown. So very often when you change into PWM operation inverter, you want to save some energy, but then motor will get hotter and eventually it will break down. So you need to select those motor will be workable for the PWM. So that's something, if in the future you want to convert many motor drive into PWM, you need to be careful about this phenomenon. So just now you may ask me how we can get the PWM. With the basic PWM, when you learn in the electronic circuitry, in the year 2, we'll be using this. All we're trying to do will be how to change that PWM. We have a sine wave there as a reference that can be come from signal or feedback from your power source. And then you have a triangular wave. When you compare the triangular wave sine wave using a comparator, you automatically generate this kind of PWM pattern. This pattern will be the same as what we require to drive the inverter. So this kind of method is naturally generated by using simple comparator. Have you seen this in the past? Using simple comparator to generate the pulse moderation? I think many people learned them in the animation. Have you learned them?
I kind of remember.
You must have learned that, but it's too long time ago you forgotten. But it's the natural method to do it. So that means you can either using computer to generate this pattern by using some equation, or using simple pulse moderation comparison, sine wave comparison. Just a comparator that will do. So other method. But of course, for EV operation, we don't use comparator. It's too troublesome. Use computer to generate. So the control method, you can see here, we got vehicle here, and we got motor drive system here. There's something I want to introduce to you called the VF control. VF control is really basic phenomenon for all the motor drive. We need to control everything based on some VF control. Sometimes we call it quantum VF control. Then the ratio between voltage and frequency are fixed constant. Why we need to do that? Mainly about the magnetic flux principle. So this principle It's quite complicated, but in simple way, I can tell you what it is. So basically, for the Faraday's law, that one we learned in the year one, right? The eventually of the magnetic flux will become the voltage generated. So that's how we generate the voltage. And then for motor itself, we only care about this one. The motor, we want the flux will be always optimize them in the maximum best performance flux. What the best performance relate to the voltage and the frequency. So we come over timing. So end of the flux. Then you can therefore optimize like that. So that means the motor magnetic flux will actually proportional to the ratio between voltage and frequency. So if I want to optimize the motor at the best performance of the flux, I need to make sure the V and F ratio will be constant. That would be good to do that. So for instance, your motor is running at 120 volts. You're using 60 hertz. This ratio must be kept constant all the time to ensure motor is best performance. So that means if 60 hertz is rotation speed with 3,600 RPM, is equivalent to 3600 C. So if now then you want to reduce the motor speed to lower speed, say 10%, then many people they just reduce the motor voltage. But if you reduce the motor voltage, you see that V over F will become lower, smaller. Your flux will reduce to 10%. The motor doesn't work. The motor best performing motor is the optimum best magnetic flux, say 0.7 Tesla. You can't change that. Once you change that, you have no flux, no magnetic flux to generate any power. So we must keep this as a constant. The way we do that, both voltage and frequency need to change together. If you want to change that into 6 hertz, this need to change into 12 volt. Yeah, together. Otherwise, the motor doesn't work. So that's so-called the basic principle for constant VF control for all the basic motor design for EV. Okay. So that's how the inverter is working. I think you all know that everybody try to use inverter for the AC. Why they? Because they're using this principle. When you want to change the AC speed compressor of the fan speed, changing different speed, you need to change both voltage and frequency together. You can't just reduce the voltage using transformer. You can reduce the voltage. You don't do that. You change all together. So that's the principle of this inverter to control the V and F together. Okay, we get that? So to control this one, we have constant VF control. Of course, VF control is basic. It has something more complicated control method of field-oriented control, which is based on VF control, but simultaneously they control magnetic flux and magnetic torque. Two ways to control that. VF control only control roughly about the magnetic flux. They don't control the torque current, they don't control the field direction. So this is more advanced method. Even though it's so advanced, that was more than 25 years ago. It was developed by professor called Peter Vance. Yeah. But he already passed away then. I think he already passed away such a long time ago. But anyway, so this field of control, I myself spent about 3 years to understand it properly in my postdoc. So in the future, if you like to do a PhD, you will follow me to do a more advanced level for the vector control, field-oriented control. Something quite nice. And after this one, we also developed another direct torque control. It's more advanced. we want to especially control the torque profile for any motor. So we convert the field control to be more dedicated control system for the torque control. We call direct torque control. So that's the history of development in the EV system. So again, that's a really basic equation for motor drive. You can see that we have something called the frequency in here, and also relate to the number of poles here. A motor itself in 2 poles is the basic motor, then 60 Hz, then rotation speed will be 3,600 RPM. But we have 4 poles, we can reduce the rotation speed by saying the number of poles. So that means the pole pair, you can use the P to control that. So that's why if 2 poles, then we got the 3,600 RPM, but if 4 poles divided by 2, we 1,800. So many industrial drive based on this method to calculate or determine the motor speed. So that's a basic equation. And then there's a term called the sleep. Induction motor using the sleep, that means the difference between the 2 frequencies. One appear in the stator, the other appear in the rotor. These 2 are in different frequency. So they use their differential frequency to generate the rotating torque. If these 2 frequencies are equal, no torque can be generated. So that's why between them we call it sleep. The difference between these 2 frequencies. If you learn electric motor, then you should have already learned that. So that's how we generate the sleep. So that means we can control the sleep, can also control the actual rotating speed for the rotor. But again, so this equation, you don't need to memorize it. I just give to you so that you refresh your memory you learn in the undergraduate. Most of students, they learn this equation in the undergraduate when they learn the electrical machine. So basically, we have the number of poles to control how to reduce the speed. We got the sleep to also control the speed. So when the sleep is equal to 0, then that means we cannot generate any matter first. Then, however, the sleep usually control to the small value, usually about 5%. Then, usually about 5%, then you got something like more like 95% of the signal frequency. Power frequency will become your rotating speed. So that's how you operate. Most of sleep, the best operation will be roughly about 5%, 5 to 10%. So most of induction motor. When the motor stands still, just starting, then the sleep will be really large. Then we don't have any magnetic torque anyway. So here will be the typical curve we see for all the induction motor. A few slides before, I only showed you this portion, without this portion. Let's do some quick revision what that portion means to us. This is really famous for all the textbook, all the lecturer will teach you about this motor drive. So we have base speed in here. This is the automatically say the motor 60 Hz, base speed maybe 60. And then we are able to control motor, have constant torque all the region from 0 speed up to your base speed. And then you can see that we are using constant rear control. So that's why when we increase the speed, we also need to increase the voltage linearly. So become rear control. Then the torque is proportional to the curve. So that's why when we want a constant torque in here, then we will maintain the current to be constant. So that you can control the torque. But now then go to here. This base at the end of the base frequency. The motor voltage up to the maximum voltage in motor is 200 volt. You can't increase more than 200 otherwise. Go up your motor winding too high voltage. So you must stop the voltage from there. Even though you tend to use constant rear control, you cannot increase voltage. But how you can increase the speed further? Voltage cannot increase. Frequency is now increasing. So from this equation, you know that V is cannot increase, only keep at 200 or maybe whatever voltage. Frequency is now increasing. The flux will be dropping. So you can see that somehow the flux could be dropping. But however, what you can do will be the current control and torque you don't want to torque to be reduced, you must try to keep the same kind of current. Then the rating of the motor, voltage and current unchanged, the motor power will not increase anything further. But however, one thing will happen, the motor power cannot increase further with your high speed. What item you need to decrease to compensate? Power into the top time different. The power of motor already fixed. You cannot overdrive the motor with higher power. Motor power, maximum power is fixed. So when you want to increase the frequency or rotation speed, the torque must be decreased. So that's why you can see the torque over decreasing in such a way. So actually, this region, that's why we call it constant power region. Some textbook, they call this region called the field weakening region. Field weakening. So in this region, the only one way we can increase the speed is to weaken the field. So of course, there's some mechanism here, you can weaken the field, but obviously you can see that in here, voltage unchanged frequency increasing the field must be weakened. You can only weaken the field to allow the motor to continuously to increase the speed. So that's called the field weakening region. So this field weakening region appear on all the motor drive system. Induction motor and also DC motor. But however, PM motor, you cannot weaken the field. The field cannot be weakened. So that's why many PM motor cannot overdrive because you cannot weaken the field. If you cannot weaken the field, you can't increase the speed further. So that's one of the disadvantages for some PM motor. We need to use other method to do that. And then I'm also given this region called the high speed region. So when the motor go to this space and then double, maybe further up, what's going to happen will be you are using this high speed performance to do that. In this case, the motor voltage is still unchanged, but we start to weaken the current and the thrust together to allow the speed to go one step further higher. But this does not quite happen in electric vehicle. Now this does, but not for normal SUV. Electric vehicle only for electric train. The electric train still electric vehicle anyway. But in here, we try to overdrive them to higher and higher speed. So we only can do is to weaken the current and the field. So that's a really popular free region of operation in many motor drive systems. Yes?
What determines that point where you can no longer only drop torque, you have to drop the current as well in order to go higher speed? Yeah, how does that, where does that cut off occur?
Yeah, that is more complicated than here. Yeah, it's not covered in this syllabus. But basically, you can see that here will be when you further weaken the field in here, then somehow your field cannot become too low. For instance, not about 30% contact increase, far too low, then the thrust cannot link to other coil. So in this case, we have a limitation. We cannot weaken the field too small because the physical geometry. So when you find that your thrust cannot further reduce, you need to reduce your current. Then that will push you to this region of high speed. So that basically 0 to 6 Hz, then proper to 120 Hz, and go further, you weaken further of your performance. But that's quite okay because when high speed, we usually based on momentum to drive the vehicle. At this time, many of the frictional torque can be reduced. You don't have the static friction, then the motor can able to run at high speed anyway. So here will be field on data control. Field on data control, as I mentioned, is really nice, really famous control system for all the electric vehicle. Everybody knows. So basically, we are separated into two kinds of the control parameter. One will be related to the thrust, motor magnetic thrust. Another one will be related to the torque. So we got two control parameters. When you control torque, when you control the thrust, we can separately control them. Why we call field on data control? Because for all the magnetic thrust, then we can further into X and Y axis to access control. X axis, Y axis, we separate the control when the flux current, when the torque current. If we can able to control separate the torque and the flux, then we can have much easier to control motor, like what we control DC motor. When you control DC motor, you can control the armature current, the torque. We can also control magnetic flux separately. So that's why here we're able to control separately. For the torque current, you can demand high torque, you can control this torque current. If you want to have different range of speed operation, you can control the flux. So that's why we have more controllability for the motor system. So this is called the field-oriented control because we can orientate the field to operate on X, Y axis, two separate control axes. X, Y, after we done that, they're completely decoupled. They're no relations to each other. You can separate to control. So that's quite nice because in the past, in this motor, if you want to control voltage, you may affect your flux, you may affect your current. So we cannot just use the voltage control independently about the motor current or the motor flux. But now they're using this control method. They got some algorithm here, we can separately control them. So that's what happened. So this diagram to show you how we separately to control them. Now in the past, when we control DC motor, then we can separately control the field, separately control the armature. So this relate the torque, this relate to the field. But now they're using flux-oriented control, we convert the control method so that you can look like control DC motor as such. So that's so-called flux-oriented control method. Then the good thing is we are able to control the flux really well, even though in the field weakening or constant power rating, we can easily to manipulate and also to control them. After we do that, then the whole motor operate in another domain. We call the field-oriented control domain. In this domain, we can therefore control two separate current, the flux current and also the torque current separately. But of course, this will go to a postgraduate level, not even in the upper division, not even in the master. When you go to PhD level, I will show you this. So another motor is called the switch reluctance motor. I always like to work on this motor. I think this motor is the best. So that's why I spent last 25 years on this motor. It's still not yet give out. I still have a few PhD students working on SR motor, still a really good topic. Anyway, SR motor, why is good? And I mentioned to you because it's fault tolerance, simple, low cost, hasn't quite developed yet, so we got more opportunity to develop. It's quite an old motor. I think it's since 1838 already some people using it to drive a local automotive. But the thing is, this motor developed well before 1838. I think some people told me the first motor in the world also switch reluctant. Of course, during that time, we don't call it switch reluctant, we don't have any switch. We call it variable reluctant. We just changing the reluctance to drive the motor. But today, we are not using variable reluctance, we're using transistors to switch the reluctance. So, but this motor is not quite developed yet, very good, mainly because powertronic. We see powertronic only developed for the last 50 years. I think in 1970, if you know the history, 1970, we only had some really basic powertronic like bipolar transistor and diode. And then only in 1985, we started to have MOSFET. And MOSFET still not powerful enough to drive the SR motor. And then in the late 90s, we had IGBT coming in. Then we start to use IGBT to drive the SR motor. So basically, SR motor can only become realistic only in the last 25 years. But the development for SR motor is still really slow, mainly because of not that mature. Don't have too many manufacturers working on this. To work on switch reluctance motor, you need really good technology for the magnetic design plus power electronic inverter. We did both. So that in that time, in this motor was too famous, so cheap, low cost. So that's why this SR motor being ignored. But however, we know the advantage is fault tolerance. So we really good applied it in the electric vehicle. Electric vehicle fault tolerance will be so important. We cannot allow any fault happen in a EV. So this motor has that capability. So basic control for S motor will same as all the other motor systems. We still need the position sensing because we need to know how to drive each winding in each location. So we do have sensors sense that. We need a current to understand the torque current. The torque still in a way proportional to the current. We can sense the current to fulfill a control mechanism to control the torque. And then again, we have some kind of converter or called inverter to drive the motor. But this inverter has different formats compared to the conventional inverter. The motor itself has quite a different configuration. So this is how the SR motor look like. And the internal will be our rotor, externally will be our stator. So the winding here, the engine. You can see that here the internal only silicon iron, only iron, without any winding. And then you can therefore rotate. So the magnetic path here, say the magnetic path, like in this path, or some of them in between this path, then the magnetic field go through this path. Then that's our magnetic reduction. The motor itself will try to energize them so the magnetic flux will go through the lowest amount of the reduction path. So we automatically search that particular path, like in here. So if they are not in that, they will try to rotate until this certain alignment, the magnetic flux can go through. The motor itself will rotate rotor by natural principle to allow the flux to go through the rotor so that the rotation can be established. So there's some special pattern between stator and rotor. They cannot be equal. If equal, once they measure up, they never can rotate. So we must make the number of poles in the stator motor are not equal, they can continue to rotate. Otherwise, 4x4, they measure up here, you cannot rotate forever because of the alignment. If they never can align 100% alignment, then we can therefore continue to energize particular winding to force the motor to rotate continuously. The funny thing of this motor will be the base of reluctance, or in a way people call it induction. The motor itself has its own inductance. Then inductance, because for the alignment, like in here, you can see that. Once they align in here, the inductance in this will be much higher inductance because the magnetic flux can go through. So that means the inductance of this winding are vary with the angle of rotation. Some angle is high inductance, some angle has lower in reluctance, like in here. When the motor and stator align in some way, you got higher alignment or high inductance, and vice versa here. So the equation we found that the magnetic torque are proportional in a way to the inductance, change of inductance. When you have change inductance, then you can produce magnetic torque. When it's fully aligned, we don't have a magnetic torque because there's no change in the inductance. So that's why this kind of motor highly rely on the variable inductance or variable in reluctance. So then in this motor, how we free rotate them, so we can continue to rotate, first have the first alignment, and next we energize another winding, alignment, and then we energize another winding. So we do it one by one, phase by phase, to control the motor to rotate in such a way. So you can also see that the motor inverter is quite different. Before the motor inductance are using two transistors for one phase, but in here we're still using two transistors. But two transistors here are included in this very manner. These two ports are not joined together, but will be used to connect to one winding. So when you energize them, when we turn these two transistors, this current will therefore feedback return to the battery. Right? Yeah. So it's quite special. Now I sketch it. So when I energize it, oh sorry. And basically we're doing this. And then for the power regeneration, then this current will therefore feed back into here. Okay. So the way we energize the winding is different from what we did before. The configuration also different. So that's one of the reasons this motor is not that popular, because for inverter motor joint, we need to specially make. All the motor joint are these two are connected, but this is special. We need to specially make. So that's why it's not that popular. So up to this point, do you have any question? It close to the end of the lesson now. So next we'll show you how we operate the SR motor about top item. And we may not have time to finish. So probably any question up to this point, then we continue next week. So today we show you briefly about different type motor, DC motor, induction motor, and SR motor. They all been used widely in electric vehicle. DC motor is conventional, and we learn substantially in undergraduate. Induction motor, we learn some. Then we learn the basic equation. Today I show you the V over F relationship and also positive operation. And now we show you the SR motor. SR motor is really important because I think getting more important in the next 5 to 10 years. And we got more research work going on in this and much safe motor. So it should be used in aircraft or maybe electric vehicle. This one special because it's based on the electric principle, not based on the magnetic flux linkage. So that's why this do have some. So that's all. Any other questions? Do you think that's too complicated or too much? No. The thing is, I'm in the exam, I will not ask you anything about equation. That is too complicated. I only ask you about the principle, how to operate, what you think, which one is better, this kind of thing. Maybe some basic DC motor, I may ask you something. Because basic DC motor, I think you all have learned them 5 years ago, 10 years ago, right? So it's more safe to ask you such DC motor, but not DC motor. Okay, see you again next week then. So again, in 2 weeks' time, we're going to have a midterm. I think I will start to give you some homework so you can start to prepare for it. My homework will be equal to my midterm anyway. Okay, so that's it. Okay, see you then.